the classical ideal gas in a microcanonical ensemble. We have already discussed what is microcanonical ensemble. Microcanonical ensemble is used to describe the isolated system for which there is no exchange of matter or energy with the surrounding. That means the energy of the system is nearly constant. For such kind of system, the energy of the system is nearly constant and it is fluctuating in a small energy window. We are going to find out the corresponding ideal gas equation using the microcanonical ensemble. So to do that, let us first define what is an ideal gas. An ideal gas is defined as a collection of particles for which there is no interaction among the particles. So consider a system of n non-interacting gas molecules enclosed inside a volume V, and since there is no interaction among the molecules, the potential energy of the system is going to be 0. As a result, the Hamiltonian of the system can be written as 1 by 2m summation of pi square. It is the complete kinetic energy of the system. Because there is no interaction, that's why the potential energy of the system is going to be 0. Now our next task is to obtain the volume occupied in the gamma space by this microcanonical ensemble. This is going to give us the total number of microstates, and once we know the total number of microstates, we can obtain the entropy of the system. And once we know the entropy, the rest of the thermodynamic parameters of the system can be obtained. So the first task is to obtain the volume occupied in the gamma space, which is given by the following integration. Phi E is equal to integration of d3np d3nq under the constant h less than E. H less than E is the surface enclosing the complete volume of this microcanonical ensemble. It is because the statistical distribution function is 1 in the small energy window E to E plus delta, and it is 0 in the rest of the regions. If we look at this integral, it has got two variables P and Q. The Q variable is the position coordinate and P is the conjugated momentum coordinate. So we will do it step by step. So first we will try to obtain the corresponding volume occupied by the conjugated momentum coordinates. In order to do that, let us first consider an n-dimensional sphere. In this n-dimensional sphere, the position vector is a function of x n number of rectilinear coordinates. So that means r is a function of x1, x2 like that up to xn. A small volume element in this n-dimensional space can be written as dvn and is the product of dx1, dx2 like that up to dxn. So this can be written as the product of the general term dxi. So the volume of this n-dimensional sphere can be obtained by integrating this small volume element in the complete region. So the volume can be given as integration of this product of all the small element dxi under the constant 0 less than equal to xi square less than equal to r square, where r is the radius of the n-dimensional sphere. Further, we know that for a 3-dimensional sphere, the volume is proportional to cube of the radius. We can generalize it to the n-dimensional sphere, and we can write Vn, that is the volume of the n-dimensional sphere, to be proportional to r to the power n. So we can write the volume of the n-dimensional sphere Vn to be equal to Cn into r to the power n, where Cn is the corresponding proportionality constant. So our task is to find out an expression for the proportionality constant Cn. To do that, let us consider S and R be the surface enclosing the n-dimensional sphere. So we can write dVn to be equal to S and R dr, and dVn can be obtained from the expression for Vn. So Vn is Cn into r to the power n. So if I differentiate it with respect to r, we can get it NCn r to the power n minus 1 dr. And this small volume element is the product of dxi's, where I varies from 1 to n. N is the dimension of the sphere. Proportionality constant Cn, let us use the standard integral, that is integration of exponential minus x square in the limits minus infinity to plus infinity, and the result of this integral is root over of pi, which can easily be solved using the contour integration. Now let us take n such kind of integral and take the product of all this n integral. So the resultant integral will look something like this, that is minus infinity to plus infinity dx1, the same dx2, like that up to dxn into exponential minus summation of xi square, because it is simply the product of all the n number of integrals. And since the right hand side is root over of pi for one integral, when I multiply it for the n number of times, the right hand side will become pi to the power n by 2. And this can be written as the integration of the product of dxi exponential minus r square, where I is going to vary from 1 to n. So this pi to the power n by 2 can be written as, now the product of I is equal to 1 to n dxi as previously obtained can be written as exponential minus r square n cn r to the power n minus 1 into dr. Here in this case the n cn r to the power n minus 1 dr is obtained from the previous slide for the product of dxi. So now it is time to further simplify the integral. So n and cn are constant, so that can be put outside the integration. So n cn 0 to infinity, because r is going to vary from 0 to infinity and x is going to vary from minus infinity to plus infinity, because r is the radius of the n dimensional sphere. So this can be written as pi to the power n by 2 to be equal to n cn 0 to infinity exponential minus r square r to the power n minus 1 into dr. Now let us use the standard integral, that is integration of 0 to infinity exponential minus alpha y square into y to the power n dy, where alpha is a constant and y is the variable. The result of this integral can be written in terms of the gamma function, that is 1 by 2 into alpha to the power n plus 1 by 2 into gamma of n plus 1 by 2, provided the value of n is greater than 1. So now let us apply this standard integral to this integration that we obtained. In this case n is equal to n minus 1 and the value of alpha is simply equal to 1. So after applying the standard integral, we can get pi to the power n by 2 to be equal to n cn half gamma of n by 2, and the gamma of n by 2 is simply the factorial of n by 2 minus 1. So the resultant value can be written as Cn to be equal to pi to the power n by 2 divided by n by 2 factorial. So that means the volume of the n dimensional sphere can be written as pi to the power n by 2 divided by n by 2 factorial into r to the power n. So now let us concentrate on the second part, that is the integration over the position coordinates. We know that the real volume dqqq in the entire space is going to be v. So the nth power of this is going to be v to the power n. So the volume occupied by the macrocanonical ensemble in the gamma space can be rewritten as v to the power n into integration of d3np given by the constant h less than e. So to simplify this, d3np will take the volume occupied by the n dimensional sphere, and to make it dimensionless, let us divide the above integral by h to the power 3n, where h is assumed to be a constant and is the product of momentum and the position coordinates. So now the relation can be written as v to the power n divided by h to the power 3n multiplied by the integration of d3n p under the constant h less than e, where h is equal to p square by 2n. So to solve this d3n p under this constraint, let us take the n-dimensional sphere in the momentum space having a radius r to be equal to p, which is equal to root over of 2me from the following constraint, that is p square by 2m is equal to e. So now the volume of the n-dimensional sphere can be written as vnp, which is equal to vnr, and in this case n is equal to 3n because the pi's are going to vary from, I is going to vary from 1 to 3n. So now the volume occupied can be written as v to the power n divided by h to the power 3n into pi to the power 3n by 2, because you are replacing small n with 3n, divided by 3n by 2 factorial into 2me to the power 3n by 2, where r is equal to root over of 2me. So we can simplify it to the given expression. So the power n has been taken out. So our next task is to obtain the entropy of the system, which is related to the number of microstates or the volume occupied in the macrocanonical ensemble with this relation, that is S is equal to K ln phi E. So if I take the logarithm of the phi E, then I can obtain the corresponding expression, that is nk ln of v by h cube pi to the power 3 by 2 2me to the power 3 by 2 minus k ln factorial 3n by 2. So now we have to apply the Stirling's approximation, under which for very large values of n, ln of factorial n is equal to n ln n minus n. If I use this to the second term of the above expression, then I can obtain S to be equal to nk ln v by h cube pi to the power 3 by 2 2me to the power 3 by 2 minus 3nk by 2 ln 3n by 2 plus 3nk by 2. This is after applying the Stirling approximation to the second term of the expression. So after a few simplification, I can obtain the corresponding entropy of the system as the given expression. Further simplification will lead to entropy to be equal to nk ln v into 4 pi me divided by 3h square n to the power 3 by 2 plus 3nk by 2. So I can rewrite the energy, the internal energy of the system in terms of the entropy. So this is just a rearrangement of the terms. So the internal energy of the system is given by 3h square n divided by v to the power 2 by 3 4 pi m into exponential 2 by 3 s by nk minus 1. The next task is to obtain the temperature of the system, which is simply given by the partial derivative of the internal energy with respect to entropy at constant volume, which is given by 2 by 3 u by nk. So that means the internal energy can be written in terms of the temperature as u is equal to 3 nkt by 2, and also we can find out the corresponding specific heat at constant volume, that is delta u by delta t at constant v, which is equal to 3 by 2 nk. Finally we can obtain the pressure of the system, which is given by minus of delta u by delta v at constant s, which is 2 by 3 u by v, which is nkt by v. So taking v to the left hand side, I can obtain Pv to be equal to nkt, which is the famous classical ideal gas equation.